Hello everyone, welcome back, and we are going to talk about reducing networks of capacitors. So this is just a quick recap from the problem we solved in class where we had a circuit starting over here from terminal A, and then of course we're moving down through the first capacitor right here, and then when we hit this junction right here we have a choice. We can either go left, right, and then to B, or we could go right and then go to B. So this point right here represents a junction where we have to make a choice. So if you have to make a choice which way you go, then we typically say that these two capacitors, C3 and C2, are what we call are in parallel configuration. And then you see then that C1 and C3, they represent a series configuration. Simultaneously, those C1 and C2 are also in series here. And so there's a conundrum there. Like I said, if we go from starting at A, and we want to end up at B, there's two choices to make at this junction, two paths to take. So we need to take that redundancy out. To take that redundancy out, the first thing we need to do is to collapse C3 and C2. Now over here on the right side of the screen, we see how to collapse capacitors when they're in parallel configuration, and it turns out they just add nicely together. So what I want to do is redraw, and it's very important that you always redraw the circuit. And so this is C1 here, and I want to redraw it so I have just two capacitors here, and this is what we're going to call let's call it 2,3, where C23 is just going to be C3 plus C2. Now looking at the new circuit, we see there's no more ambiguity. If I start at point A and move through to point B, there's only one choice of a path to make, and that means that C1 and C23 are now in series configuration, and then if they're in series, to collapse them to one single capacitor, I need to use the reciprocal law, the way they add in reciprocals. So in other words, the final capacitance C equiv, or you could call it C1, 2, 3, will be 1 over C1 plus 1 over C2, 3, all to the -1, or 1 over that whole fraction. So let's write this out. So I have 1 over C1 plus 1 over C2 plus C3, all to the -1. And let's plug in some numbers. So we know C1 up here was 12 microfarads. So I have 1 over 12 plus 1 over, and then C3 was 1, and C2 was 3 microfarads. So I have 1 plus 3, all to the -1, and my final unit should be, again, microfarads. And let's see what we get for this. Let me step over here to my Mathematica notebook and type this in. So I have 1 over 12 plus 1 over 1 plus 3, and I get 3 microfarads as my final answer. Now the key concept here again was realizing realizing what we had to do in terms of collapsing which two. So if you look again, look at C1, and now again C1 is in series with C3 and is in series with C2, and that's a problem, okay, because we have two choices, or there's an ambiguity. So if I was going to collapse this using the series laws, which one do I do first? Do I do C1, C3 first, or can I choose C2 and C1 first? I don't know. I don't know which one to do. And so that tells us to get rid of that ambiguity, the right step, the correct step, the first step is to get rid of the ambiguity by collapsing the parallel circuit using the parallel, the way capacitors add in parallel. So that's the key concept for this problem, for any network of capacitors that we're going to reduce. So let's try out another one. So here I have a capacitor network, okay, and I want to reduce this total network into one capacitor C equiv. So that's our task. Now look at each two capacitors. So I have here one with 0.25 farads, 0.4 farads. So that's capacitor AB and capacitor C and D. And if I'm coming from here and I want to move this way, you see here I have a choice to move this way, or I can move this way, and then here again I have a choice to move either way to get to the end over here. So again, I want to reduce the ambiguity. How can I reduce the ambiguity? Well, what we can do is partition. I know I want to get from here to here before we can hit this capacitor network. So just going from here to here, I have two ambiguities just to get to here. So let's collapse this one over here. So what I want to do is write this as one capacitor, and now remember it's in parallel, so look over here, up here in parallel, the capacitors just add. So that means this capacitor here is going to be 0.25 plus 0.4 farads. And here we have 0.35 farads and 0.5 farads. Okay. Now the next step I can do is address this last ambiguity here. Because again, if now going from here to here, there's no more ambiguity, but here I'm going to hit another ambiguity. I can go either way, and I don't know which way is right. So what I want to do is just collapse this to get rid of the choices of paths. Collapse that network. So here I have 0.25 plus 0.4, and then I'm going to reduce that to 0.35 plus 0.5, and I just add them straight up. Again, we are in parallel. But now, look here, now we have the last configuration where they are in series, and when they are in series, we have to use the reciprocal law of adding them together. So in series, the final network should look like this, where this one here is C equiv, or the equivalent capacitance, and so we have C equiv is going to be 1 over 0.25 plus 0.4 plus 1 over 0.35 plus 0.5 all to the negative 1, and the final unit will be farad. So let's take over here. So we have 0.25 plus 0.4, and here we have 0.35 and 0.5, and let's keep well, we should keep one sig fig, so we'll have 0. But I'll just keep 3 just for record's sake. Okay, again, same concept. We want to address the ambiguity. We want to use our addition laws for capacitors in either series or parallel. Let's look at another example, problem of the day sheet. So problem A, problem 1, part A, compute the equivalent capacitance and the following scenarios. So we have A and B, so we have two network of capacitors. So let's look at this one. So this is a little tricky because notice what happens is if I start at A and I go over and I want to arrive at B, I already have an ambiguity here. I could go straight down here, arrive at B. I could go through this point, and then here I have another choice. I could go this way, or I could come this way. So this point and this point right here, which one? Those are the two ambiguous points where I have a choice of path to make. So which one should I address first? Well, look at this point. If I address this one first, is this capacitor in series or parallel with this capacitor? Is this in parallel with this? It looks like it, and it's in parallel with this. So I'm not sure here what these configurations are at this point. They all look weird, but what we do know for sure are these last two. There's no doubt in your mind that those are in parallel. So if there's no doubt that those are in parallel, get rid of them first. Okay? Tackle those first where there's no doubt. So again, very important to redraw the circuit of what you're doing. Okay, this is still C, this is C. But this one over here is going to be, and okay, so they're in parallel, and remember, keep going all the way up here. In parallel, or here, they just straight up add. Okay, so that means it's going to be C plus C is 2C. And in this case, in this problem, C just represents an arbitrary capacitance. However, all capacitors in the network have the same value, C. So this is nice, and since we addressed the ones where there was no doubt as to what configuration they are, it made the circuit easier to look at now, because what you see here, again, we have an ambiguity here, but these two are definitely in series. There's no doubt. I'm still not sure. About these two capacitors, and I'm still not sure what these are. They could be parallel, right? This one could be series. This one looks like parallel, but then this one's in the way. So I'm a little confused there, right? But no doubt these last two are in series. So if those last two are in series, collapse them. Okay, so I'm going to rewrite my circuit to look like this. And I know this one is still C, but this last one is, and since they're in series, we have to use the reciprocal law. So I'm going to have 1 over C plus 1 over 2C to the negative 1. And finally, the last one, and what I should say is, now that you've addressed these two that were definitely in series, look what we have. We have a nice, no more ambiguity. Well, there's still an ambiguous point in terms of moving from A to B. I can go this way and this way, but the configuration of the last two capacitors here are definitely parallel. So if they're definitely parallel, they just straight up add, so I end up with my last circuit here. And if they're in parallel, they add, so this capacitance will be C plus And then we got to be careful to keep track of everything. And this will equal, I'm sure we could do this in our minds, it'll be C plus 1 over C and 1 over 2C. So 5C over 3. So that's your answer. Okay, let's look at this last one. Same principle. Let's look at going from A to B here. Again, we hit this junction here, and I can go this way, or I can go this way. So that means here's my junction where I have to make a choice. And look, these last two capacitors are definitely in parallel. These two are in series, but simultaneously these two are in series too, so that's ambiguous. But these last two are definitely in parallel. So let's address those last two. So I'm going to redraw my circuit where there's only one capacitor here at the end. I have 3 farads, and this one was 2 farads. And in parallel they add, so I'm going to have 2 plus 1 farads, which is 3. I can do that in my head. Don't need Mathematica. That's really nice because look, eliminating these last two, now we have one circuit. There's no more ambiguity. I have only one path to take. That means all 3 capacitors that are remaining are in series. And series, we have to use the reciprocal law. So my last circuit will have one capacitor in it. And the reciprocal law says I will have 1 over 3 plus 1 over 3 plus 1 over 2, 2, all to the inverse 1, or to the 1 over that. And my final unit will be a farad. So let's take a look at this. Let's get rid of that one. And I have 1 over 3 plus 1 over 3 plus 1 over 2. And the unit was farad. So I have 6/7 farad. And of course, if you want it in a decimal, we could do that as well. We'll just keep track of 3 for now, even though it should just be 1, but just for fun. Okay, that'll conclude our discussion on capacitor networks for now.